Hello, my name is Shayan Akbar. I am a co-author of this MSR 2020 research paper called A Large-Scale Comparative Evaluation of IR-Based Tools for Bug Localization. My co-author is Professor Avi Kak, and in this video, I will talk about the findings of our paper. We focus on the problem of IR-based bug localization, and we're given a large corpus of software repository and a bug report query. The goal is to rank the source code files according to their relevancy to the bug report query. Here is a table of contents. We'll first start with the motivation and introduction to the problem. We'll then discuss past 15 years of research in IR-based bug localization as divided into 3 generations. We'll select 8 retrieval algorithms from these 3 generations in order to perform experiments on the BugsBook dataset. BugsBook is a large and diverse bug localization dataset that we have created for this purpose. We'll then present our results and conclude with some future works. So why do we need yet another study on IR-based bug localization? And mainly because past studies have mostly relied only on Java software repositories, and their datasets only consisted of few thousand bug reports that belong to very few software projects. In contrast, we have created BugsBook, which is a novel, large, and diverse bug localization dataset containing over 20,000 bug reports that belong to 29 different software projects. These projects are written in Java, C, C++, and Python programming languages. If we look at the past 15 years of research in IR-based bug localization, we can see that we can divide it into 3 generations. And each generation will tell you a story of what happened during that generation in the field of IR-based bug localization. We compiled a list of prominent papers from these 3 generations and selected 8 retrieval algorithms from them. We then conducted experiments on the BugsBook dataset using those 8 retrieval algorithms in order to evaluate the relative performances. So what are these 3 generations of IR-based bug localization? From the year 2004 until now, we have seen many papers in the field of IR-based bug localization. On this slide, we have shown only few of them. From 2004 until 2011 was the first generation of IR-based bug localization. The research in IR-based bug localization during that generation was still in its infancy, and most of the early works were done during this generation. From 2012 until 2015 was the second generation of IR-based bug localization. The focus of research mainly in this generation was toward extracting software-centric information from repositories in order to enhance bug localization. From 2016 until now is the third generation of IR-based bug localization, and the main focus of research is on modeling interterm semantic, proximity, and ordering relationships. As we have said, first generation tools mainly depend on traditional bag of words-based modeling. The second generation tools extract software-centric information such as bug report history, version history, structured information embedded in bug reports and code files in order to enhance the performance of bug localization systems. The third generation tools are mainly about modeling interterm proximity, order, and semantic relationships. Here we show 8 retrieval algorithms that we have used in our paper. The first two are TF-IDF and Dirichlet language model. These are the first generation tools that we have used. Next are BugLocator and BlueIR, which are second generation tools. Then we have 4 third generation tools, which are Markov random field-based sequential dependence and full dependence models, forward semantic model or PWSM, and source code retrieval with semantics and order, which is SCOR retrieval algorithm. The first generation tools depend on simple bag of words based modeling. TF-IDF is an example of this. TF-IDF works by combining frequencies of individual query terms appearing in the source code file and their inverse document frequencies in the corpus, which is a software repository, in order to determine the relevance of a file to a query. On the other hand, retrieval language model estimates a first-order probability distribution of the individual query terms appearing in the file to produce a relevance score for a file given a query. The third generation tools are BugLocator and BlueIR. BugLocator accounts for historical bug reports to enhance bug localization, whereas BlueIR extracts code entities like class names, method names, and variable names, as well as comment blocks in order to help in localizing the bug. The third generation tools model proximity and order relationships between terms. MRFSD and MRFFD are examples of these tools. These tools go beyond simple bag of word based modeling. And instead of considering individual query terms appearing in the file, they consider pairs of query terms appearing in the file. For example, MRFSD estimates a probability distribution of the frequencies of pairs of consecutively occurring query terms in the file to compute the relevance score for a file given a query. On the other hand, MRFFD considers frequencies of pairs of all query terms appearing in the file, or frequencies of all pairs of query terms appearing in the file to determine the relevance of a file given a query. Third generation tools also model semantic. But before we discuss how to model semantics in the retrieval process, we need to discuss what are semantic word embeddings. Semantic word embeddings are semantic vectors or semantic vector representations for words. When Word2White paper came out in 2013, it brought a revolution in the field of textual processing. Word2White neural network takes in as input millions of documents and generates a semantic vector space. In this vector space, each word is represented by a vector, and semantically related words are clustered together. For example, one cluster could contain terms like write, output, and close, whereas another cluster could contain terms like polygon and shape. We have used SCOR word embeddings in our paper. These word embeddings can be found on this link. SCOR word embeddings contains semantic word vectors for 500,000 software-centric terms. But how one can use semantic word embeddings for retrieval? On this slide, we have shown how one can use semantic word embeddings in retrieval as proposed in the SCOR retrieval algorithm. On the left, you see in purple, query word embeddings 2D array and file word embeddings 2D array. Each row in this 2D array corresponds to a word vector for a query term, and each row in this file word embedding 2D array corresponds to a word vector for a file term, TI. We then compute pairwise cosine similarities between query term embeddings and file term embeddings and generate a match layer 1 2D array. In this 2D array, each cell corresponds to a cosine similarity value between a pair of query and file term. Match layer 1 is then subjected to a series of filtering operations in order to generate a scalar value that we call SCOR PWSM. Match layer 1 is also subjected to a convolutional operator using a specially designed kernel which has non-zero values on its diagonal and zero values in the off-diagonal elements. After performing a convolutional operator on this match layer 1, we generate a match layer 2. Each cell in this match layer 2 corresponds to a similarity value between a pair of query terms and a pair of file terms. We apply the same filtering procedure on the match layer 2 as we did on the match layer 1 and generate a scalar value that we call SCOR ordered semantic model or SCOR ORD SM. We will use these scores in the next slide. To generate the relevance score for PWSM retrieval algorithm, we use the retrieval language modeling score and PWSM score in a linear combination. whereas SCOR is dependent on 4 retrieval scores: Restricted Language Modeling Score, Sequential Dependence Score, PWSM or Pervert Semantic Modeling Score, ORD-SM or Ordered Semantic Modeling Score. On this slide, we show a table of logic components built into each of the 8 retrieval algorithms. The columns correspond to the retrieval algorithms, whereas the rows correspond to the logic component. We perform experiments using these 8 retrieval algorithms on the BugSpoke dataset that contains 20,000 bug reports belonging to 29 different software projects, which are written in Java, C, C++, and Python programming languages. Just to compare BugSpoke with the past bug localization datasets, we can see that the number of bug reports in BugSpoke is over to 20,000. This is the largest bug localization dataset as available online. On this slide, we show the number of bug reports statistics for the bug localization for the BugSpoke dataset. We show that we have in BugSpoke many Apache Java projects, other Java projects, and C, C++, and Python projects. The total number of bug reports present in BugSpoke is 21,253. Here's a construction pipeline for BugSpoke dataset. We will now show the results on the BugSpoke dataset. We mainly performed 2 experiments in this paper. First one is about evaluating the performance of retrieval algorithms belonging to different generations. Second one is about evaluating the effect of semantic word embeddings in the retrieval process. Here are some highlights of the paper. Third generation tools are most effective in terms of retrieval precision. SCOR word embeddings, which are trained only on Java programming language projects, can be used for retrieval in other projects belonging to other programming languages like C, C++, and Python. Another thing that we have noticed in the paper is that the size and type of semantic word embeddings do not affect much the performance of retrieval algorithms. Here we show the results on Java-only software projects in terms of mean average precision or MAP values. We see that SCOR, which is a third generation tools with a MAP value of 0.4, outperforms all other retrieval algorithms. On C, C++, and Python projects, we see that SCOR and Markov random field-based sequential dependence or MRFSD retrieval algorithm, both third generation algorithms, outperform all other retrieval algorithms. On all projects, Java and non-Java, we see that that SCOR, which is a third generation tool, outperforms all other retrieval algorithms. In this paper, we also notice that there is a cross-utilization of word embeddings across different programming languages. SCOR word embeddings were trained only on Java projects. But when we applied these SCOR word embeddings to search in C, C++, and Python projects, these projects are Chrome, OpenCV, Pandas, and TensorFlow, we noticed that there is a significant increase in the performance in terms of mean average precision values. We also noticed that there's little to no effect in the changing semantic word vector size, as well as word embedding algorithm. On 4,000 bug reports of Eclipse dataset, we noticed that even if we change the semantic word embedding size from 500 to 1,000 to 1,500, the mean average precision value remains approximately 0.32. We also trained other semantic word embedding algorithms like GLOVE and FastText on the SCOR word embedding data on the SCOR dataset. and we noticed that is still the map values, and we apply and then we applied the um, and then we applied the semantic word embeddings for retrieval using SCOR algorithm. We noticed that the retrieval performance is still 0.32. To conclude, we can say that the third generation tools are far superior in performance. SCOR word embeddings are very generic, and it is time to merge second and third generation tools to produce a hybrid approach. Thank you. Please let me know if you have any questions.